Okay, continuing on here, we just finished up the Valreg processing block and we evaluated the EPI to anat and the EPI to EPI registration as well as the extents mask. So let's continue on here. Going back to our proc script, here's the end of the Valreg block. If I go down, we get to the blurring step and then the masking step. So let's try to cover those a bit now. The windows, where are we here? On the bottom controller, our underlay is the T-shift result. So we'll manipulate that next. But let's set our top controller then to be the back to the results from 3D Valreg. So the underlay can be pb02 run1.valreg, which I guess it was, and I'll close the actually I think I'll even close the axial image and then reopen it so that it's the original size, or is that too small? I don't know. Details. And let's open our graph window, and I'll make that the same height as the one on bottom since I've made my screen a little lower resolution. And I'll right click in the image window and I'll jump to XYZ to the coordinates we had saved before. 24, 86, 14 in, so those would be Tayloric space coordinates. Actually, to be clear, they would be TTN27 coordinates, which is a specific template in Tayloric space, the column brane. So there again, there are our Valreg results. We can set set controller B then to be the output of the next step. So going back to the proc script, the next step is blurring. And why do we blur? We blur for two reasons. One I've talked about already, just in the resampling step. We blur so that with neighboring voxels, combining neighboring voxels a little bit, you hope to get some noise cancellation and hope to make the signal a little more clear and to possibly give you a little more clear results that way. The other reason we blur is when we go for the purpose of group analysis. When you're doing a group analysis, even with nonlinear registration, you don't always get perfect anatomical alignment between structures, especially if neighboring structures have similar contrast. Getting them to line up perfectly is asking a lot, even with nonlinear registration. So imagine, for example, along the cortex, someplace you locally have 4 folds in one subject and 3 folds in another subject, and those can't possibly register perfectly. So so another reason to blur is so that the blobs, each single subject's, say you have a statistical cluster, that blob, if you blur it a bit, can be a little bigger, and then they will overlap better at the group level. So let's just see the effect here. When we blur, I like to I would suggest not blurring at all, or if you're going to blur, typically, which we usually do, if you're going to blur, I would tend to blur a full width of half max of between 1.5 and twice the voxel size. So twice the voxel dimension would be on the large side of a blur, in my opinion, especially with nonlinear registration. And then 1.5 would be, a more gentle blur. And keep in mind that the less you blur, if your group analysis will use clustering, then the less you blur, the less the smaller your clusters will need to be at the end. So if you don't, pluses and minuses either way. But again, 1.5 to twice the voxel size. Remember, a full width at half max is a diameter. So if 4 millimeters is the full width at half max of a Gaussian kernel, that means the radius at half max is 2 millimeters. So in our case, the voxels are the original voxels say are 2.75 by squared by 3. We're kind of, we're kind of in the 1.5-ish range here for a full width at half max. And, at that means at a 2 millimeter radius, you get half the contribution that the central voxel contributes to the output result. So the result at one voxel will get 1 times the current voxel plus half of the first neighbors, etc. If this is twice the voxel size, or that is to say, if the radius is equal to the voxel size. So since this is less, that gives you a feel for how strong the blur should be in this case. So with that blur amount, we're going to take as input the Valreg results, and the prefix for the output will be PB03, and then for each run, and then the blur level. So let's look at the effect of that. Controller A has the Valreg result, and let's set controller B's underlay to be the blur result. I'll scroll down a little bit here. So tcat, tshift, and Valreg are done, and now we can go to PB03 run 1 dot blur. And looking at the image, yep, that's blurrier. And then looking at the time series, of course the time series will change a bit because you're blurring, you're adding in contributions from the neighboring voxel centers. So these time series look much cleaner right here than the ones above. We are in the exact same place in the brain. It's just at each voxel we took the original one, and we have contributions from all the neighbors, given the Gaussian blurring kernel. So you notice these spikes up here in these 3 time series, and even in the lower left one, those are smoothed out quite a bit here. So that's an effect of blurring. But otherwise, the values are around the same range. So going back, that's enough look at the blur. It's not too hard to understand. Now let's look at the masking step. Remember, by default at least, AFNI does not apply a mask to the EPI data other than the extents mask. And the extents mask was only applied because we don't necessarily have data at every time point in a time series, so we don't want to jump back and forth between valid data and 0. So we've already applied that masking step. That's already done up in the Valreg block. So here we're just going to compute some extra masks, and then for the most part promptly ignore them. But let's take a peek at some of them. Usually they're used for quality control at this point in time, unless you do a blur and mask operation. That would have an effect. But first of all, we run 3D auto mask to create one mask for each run, and then we use 3D mask tool to take the union of that across all 3 runs in this case, and that's what's called full mask. So full mask is the union of each run's auto mask, without any special options here. So let's take a look at what that looks like. If I set my overlay to be full mask, I'll just do it in the, I guess I can do it in the, so on the bottom is the blur, on the top is a Valreg. It doesn't really matter so much. But I'll set my overlay to be the full mask data set. And I promptly see nothing, so I'll turn see overlay on. I'll toggle it on. And beautiful. If I go over the window and toggle O, the O key for overlay, Oh, that looks fantastic. It looks whoops, that's you. How do you spell O? That looks like it fits the data set perfectly. Why would we want anything but this? Well, let's see what this mask looks like on top of the anatomy, just to see something else. If I set my underlay to be, let's go for a nat final. Actually, let's go for the nat with skull. Why not? We've got a skull. It's nice to use sometimes. So our overlay is still full mask, so we'll leave it with that. And now let's toggle the O key. And now we get a more complete picture of what the mask covers. And oh, I see some stuff missing here. So the mask is not perfect. And what this gives us is, to some degree, is an idea of where we have signal dropout. Well, at one level we have coverage. The coverage doesn't go all the way down to the cerebellum in this case, for example. But out here we see these areas, we seem to have signal dropout. And those might be like above the nasal area and stuff where you've got a tissue and air interface, and that tends to lead to dropout. And you get a more accurate idea. Another mask that we created here, where's the proc script, is the anatomical mask. And we created the anatomical mask by just taking, first of all, we had the skull stripped anatomy input into 3D resample, and we resampled it using a master. The full mask dataset is the master. That is, we changed the high resolution grid data, the grid of this dataset to be one that matches the EPI. And then we use 3D mask tool to dilate 5 times and to erode 5 times. Dilate and erode plus and minus 5 as dilation values. In order to, and then we fill in the holes. So we use this to dilate and then erode means you're going to connect things that are like almost connected. Erode and then dilate is used to chop things off. Dilate and then erode is connecting things. So we try to fill it in, and then we have an extra fill holes option that if there are any holes inside the volume, we fill them in. And we take the previous input, and now we call that mask anat. So let's look at that. I'll set the overlay now to be mask anat, might be higher up. Mask anat FT. And that looks like a very nice brain mask. So how do they compare? And remember when we ran, it's hard to remember all of this stuff, but when we ran AFNI Proc, we had an option down here called Mask EPI anat. In that case, we're actually asking AFNI Proc to intersect the EPI and anatomical masks and make a new one. So we kind of have 3 masks going on here. So let's see what these look like. First of all, I'm going to set my underlay to be, let's say, the anatomical mask. And now I'll set my overlay to be the EPI mask, just full mask. And there you can see a pretty clear difference. Now a few things that we notice. One, it looks like right here you can see, if I drop down the opacity and make it more transparent, you can see that the EPI mask sticks out above the anatomical mask. It could do that, or it could stick out in front. It's not always going to perfectly be contained in it. So where does that happen? If we go over there and take a look at it, you can see that's probably a distortion. So you can see this part here. I don't know if you can tell that well in the video. You see it kind of sticks out in front right here. So do you want to include that or not? So that's a result of this distortion probably, and I'm not sure whether you want to count this as part of your mask. So what we do with the mask API anat option is we intersect these two masks and we make a new one called mask API anat, deviously enough. And there's the intersection. Now this is a proper subset of the anatomical mask. Well, it's obviously a subset of both of them. But this is what we're calling brain in this example. Note again that we're not actually applying this mask to the API data. We're not wiping out everything outside of this. We are just using this for local statistics like full width at half max measures. Where we might use this is going to group space. Like how do you create a group mask? We might use the anat API masks and then take some sort of intersection or a 70% intersection or something across all of our subjects. That's a separate topic. But anyway, there you go. We have a bunch of masks that were created. We calculated dice coefficient. Here's our dice coefficient computation. That's between the API mask and the anatomical mask. So that's done before computing the anat API mask. We also calculated dice coefficient between the anat and the group mask is made from the template. That's just a binarized template data set. And that's it. So why don't I stop here and then I'll continue on with the scale operation and then lead into regression next time.